In this video, we're going to look at generating a target track. I'm going to create a target track segment from bearing data to represent a period of straight line motion. And this can be interpreted as a manual target motion analysis solution, a TMA solution, by Debrief. Now we'll be using the nonsuch plus data DPF file, but in this tutorial we'll be concentrating on the plot so you can close your grid editor if it is open. A capable analyst will be able to recognize a couple of periods of steady bearing rate that lend themselves to being the basis of TMA solutions. The first period of cuts we're going to be using here are the first 15 or so sensor cuts. If I zoom in a little bit, you can see that at the end of this 15 cut period, there are two bearing lines very close together, and then there's a gap. And this is then followed by a small group of these three bearing lines, and then there's another gap. And then after this second gap, there's then a period of about 10 unsteady cuts, and then we have this steady period again. And we'll be using that for a solution a little later on. Now, experience shows that since ownership is steady throughout this period, these bearing patterns indicate that the subject vessel was on a straight course. Then it maneuvered, and then it assumed a second straight course. So to make this first solution easier to see and work on, we're going to change the color of the contacts. If I zoom in to the last bearing fan of steady cuts, this one here where my mouse is, you can see there's two close together here. So if I zoom in so we can see where the last bearing fan data point for the steady cuts is, you can see that this is the one that we need to select and identify. So I'm going to double click on it to select it. And as you can see in the outline view, it's selected this point. So if I hide that selected item, you can see that's the one in the plot editor. So if I now scroll up to so I can see the first one, hold down the shift key, then click on the top center item, then I right click, multiple items, color, and then I'm going to select orange. And now if I fit to window, I can see much easier the data that I'm going to be working on. So now we're going to be creating a solution from this selected data. And when we generate a TMA segment based on sensor data, Debrief creates a track segment of steady course speed data points, with one data point at the time of each sensor cut used to generate the segment. And Debrief has a generate TMA wizard to help us with this. So with the selected data cuts, if you deselected them, just reselect them again, right click and then select generate TMA solution from selected cuts. And then the wizard will start. So we're going to enter a range of 1 nautical mile from the ownership to the start of track. We're going to leave the bearing of 300.8 degrees as is because this was picked up off the actual bearing data itself. Then we click on next. We're going to enter a 220 course and an estimated speed of 6 knots. And then we click on finish. And then you will see the TMA segment added to the plot editor. And there we go. Here you can see the positions and the TMA name. So we'll now look at the track data for this TMA solution in the outline view. So I'm just going to expand the outline view a little bit, close the sensor data, scroll up, close all the positions for track nonsuch, and here I have track TMA 220415.22. If I left click and expand track TMA, if you look at the icon for this particular child item, you can see that it's showing a straight line section of data with a tiny red compass rose on it. However, if you look at the equivalent in track nonsuch, you can see it looks like 3 turns, but that's just the way the icon displays, and it's just 1 turn, almost a 180-degree turn. One other thing to note is on the plot, the name of track nonsuch is actually given in italics, and this denotes that it's not based on actual position recordings. So now we're going to view residuals, and to do this we need to indicate to Debrief which is the ownership track and which is the target. And though Debrief can hold many more than 2 tracks, we must still inform it which ones we want to compare. So in the outline view, left click on track nonsuch and then click on 1 on the view toolbar to make this the primary track. Then click on track TMA and then select 2. And now if we switch to the track tote, we can see both tracks are now on the tote. So now Debrief knows which tracks we wish to compare. We can now manipulate the track segment to minimize the bearing and the frequency residuals, as we did before. But first, let's look at the bearing residuals view. So if I click on Drag Track Segment, then my bearing residuals view will display. Again, as before, you might want to resize this to make it larger. And then you can see that the bearing residuals title here is bearing error. And the aim of this is for the analyst to reduce the residual error, as we explained before. And the residual error is the error between the measured and the calculated bearing. And we do this by manipulating the track manually in the plot editor. As this is carried out, a real-time view of the track manipulation is displayed in the bearing residuals view. And this manipulation is actually carried out using one of the translate, rotate, stretch or shear modes on the bearing residual view toolbar, in conjunction with Debrief's drag track functions, which are located on the main toolbar. So when you've selected your drag mode and started to manipulate the active track in the plot editor, the resultant effects will be seen in both panes in the bearing residuals view: absolute degrees and error degrees. And the aim here is to drag or position the active track to reduce the calculated error to a minimum. Obviously, the end result would ideally be 0 degrees, but that's not always going to be possible. So now we're going to manipulate the track segment. So if I click on shear, and then I move my mouse over and select the track, as you can see, the bearing residuals view now gets populated with the track information. So I'm going to zoom in at the start point, and as you can see at the moment, it's looking like there's approximately 8 degrees of error. You can see better in the error degrees as opposed to the absolute degrees. So if I zoom in on the error, that's what we've got. Now, I can't manipulate anything here. I have to do it in the plot editor. So first of all, I'm now going to zoom in. And bear in mind that these bearing fans is actually recorded sensor data. So even though the track is showing it here in the first point where my mouse cursor is, this needs to be on this bearing line. So the first thing I need to do is position it on the bearing line. And as I start moving it, you can see what's happening to the error degrees as I get closer. I'm now at a minus 0.04. So again, back in the plot editor, I zoom in. I want to get this onto the bearing line. And there we go. And then I'll zoom in again. And just see if I can get that. Oh, that's pretty good. There we go. That's showing us practically a 0 degree error. Look, it's going to be harder to, I'll have to play about with that a bit more to get that. There you go. It's dead on, in fact, it's dead on 0.00. So now I'll click on Fit to Window. I'll zoom out by dragging bottom right to top left in the bearing residuals view. And as I can see here, I have a huge error margin between the measured course and the calculated course. And it's looking like 60 degrees out. So 60 degrees, I mean, this is on a bearing, this is on a course of 220, remember. So 60 degrees is either going to be 220 minus 60 is 160, or plus 60 is going to be 280. Now, if we had narrative data and the vessel was coming on a course of 160 degrees, then it's going to be coming towards us. And something like that would perhaps be in the vessel's log to indicate this, a collision course even. So my guess is the vessel has turned away and is going to be towards 26 to 280 degrees. As you can see, I'm just trying to align this. There we go, it's around about there. It's like 250, so that's like a 30 degree change. So now I can zoom in. And again, I need to position this sensor point onto the bearing fan. So I'm approximately minus 0.5, just under, out. So as I move this now to the bearing fan, you can see how accurate that is. There we go. That's pretty much spot on out here. I'll zoom in a bit more. There we go. I mean, it's negligible, isn't it? I'm not going to be able to get that. That's pretty good, certainly for the purposes of this video. So then I'm going to click on the 180 just to show that again, and there we go. Got a pretty good result. Now for this I used the shear mode. There are 4 drag modes in the bearing residuals view, and these control how you drag the track. They're labeled and have functions as follows. The translate button means you can drag either end of the track. So I can drag either end of the track, but I can't drag in the middle. And this changes the range and bearing from the source, but maintains target course and speed. Now with the rotate, I can drag either end of the track, and doing so maintains the target speed but changes the course. I can also drag a track from the middle in this mode, but when rotate, stretch or shear mode are selected, a translate operation is performed. However, the button doesn't switch to translate in the bearing residuals view. With stretch, I can drag the ends of the track, or I can also drag the middle of the track. And stretch allows you to maintain the target course but changes the target speed. If the center point of the track is dragged, the track moves in and out, adjusting as necessary to adhere to the start endpoints on the host platform bearing fan. And with shear, as I've just used that, I can drag either end or the middle of the track, and this option allows me to change both target course and speed. Please note, while translate and rotate operations are available for all types of track segment, only stretch and shear operations are suitable for application to straight line TMA segments. This is because the sums just get too complex when applying these operations to real track data. And to help you, we have the hotspot on the tracks, where the hand cursor will only turn green over straight line TMA segment hotspots. And as you've just seen, though you select the drag options in the bearing residuals view, you actually do all your dragging in the plot editor itself. So that's us finished with the first TMA segment, and in the next part of the video we'll go on to generating the second TMA segment.